Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and the paper we are dealing with is data structures, and in this module we are talking about hashing and hashing functions. In the previous module also we had spoken about hashing, but here we are introducing the concept of hashing functions. These are the people responsible for the creation of this module, and the learning objectives of this modules are the following: to explain the concept of a hash table, what is the meaning of a hash table, to discuss the hashing algorithms and hashing functions generally, and then we are going to talk about the properties of hash functions, hash code maps and compression maps, and finally we are going to understand the concept of universal hashing. The keywords associated with this module are hash table, hash function and universal hashing. So, now let us start. Before we introduce the concept of hashing, we have to talk a little bit about dictionary implementation. If you remember previous two slides, we are talking about priority queues and dictionary implementation, and in the previous module we are talking about hashing. So, dictionary implementation is a very important concept of data structures as well as computer science in general, and when you talk about dictionary implementation, you have two types of implementation. One is used using array based and one is using a chain of linked nodes. Within array based you have unsorted and sorted, and within chain of linked nodes you have unsorted and sorted. So, in array based you have linear search and no shift is needed for addition and removal. Binary search you have to shift entries, and for chain of linked nodes again it is a linear search with no shift, and for chain of linked nodes sorted also it is a linear search early exit type of no shift needed. But most operations in any of these implementation require of the order of n except for search on a sorted array. So, this is a problem that we are trying to solve using hashing. So, when you create a dictionary using a hash table, what happens? That is what we are going to discuss in this module basically. So, the hash table is a solution. What is the solution for? The problem is that the search time is of the order of n. If you remember, in general in data structures we were talking about how the search operation, depending on the operation you have to design a data structure, and as far as the dictionary application is concerned, the most important operation there is the search operation. Okay. So, that search operation we are trying to optimize, or not optimize exactly, to reduce the time, make it more efficient. So, the hash table is a solution to make dictionary search efficient. So, we want to try to get of the order of 1 every time we do a search. Okay. And the space may be of the order of n plus n, n is actually the number of entries, where and n is the size of the table. So, n is the number of entries and n is the size of the table, the hash table that we are talking about. So, in an ideal hash table structure, it is an array of some fixed size containing the terms with key. Now, this key is the important concept of any hash table that will be used in computing the index value of the item. Normally, we do not store it using the array index, we use it we store it using a key, where key would be the index to the item. So, that is how we do that. The items are stored in a hash table and they are indexed by values from 0 to table size minus 1. So, the table size is important, the size of the table, and depending upon the size of the table, the items will be indexed to one of the entries in the table from 0 to table minus 1, and the index will take you to that. Okay. And like an array, but with a function, it is similar to an array, but with a function to map the large range of keys to a smaller range with which is nothing but the table size. Okay. So, that is the dictionary using hash table. So, we will go more in detail. What is this hash table as far as a computer science angle is concerned? It is method to locate data quickly, which is why we started off with, where we wanted the search operation to be done faster, and it is a widely used technique for implementing dictionaries. Why it is important for dictionary? Because as I already told you, dictionaries require search more than any other operation. Search is the important operation in a dictionary. So, ideally, as we already told, we want it to take of the order of 1 the search time, but it is not that hash table is a solution for everything. It is not suitable for range queries, because you are not sure that all the elements will be stored in a contiguously. So, that way it is not suitable for range query. So, what is this hashing? Okay, though we have discussed a little bit in the previous module. So, hashing determines the index using only a search key. So, hashing uses an index of a search key, and hash function locates the correct item in the hash table. So, we are now going to talk about this hash function. What is the function of the hash function? I mean the hash function locates for you the correct item in the hash table. So, we normally say it maps or hashes to the entry, the value. So, now let us take where is the application of this hash table in when you want to find out the word occurrence statistics for operations like insert and find. Dictionary, normally you use it for insert, delete and find. Find is very important. Is it necessary to do an order of log n comparisons? We should not have to do that. So, hashing, the basic plan is create a big array for the items to be stored, okay. Then use a function to figure out the storage location from the key. So, that is where the hash function comes in. So, you have a big key where the items are stored and you are going to use a function to figure out which is the storage location and what are you going to use that, how are you going to figure it out from the key and a hash function, the hash function of the key. So, that is what we are going to do, and obviously this we will talk about this in detail in this session and in this module, and also in detail about in the next module. More here we will just introduce this concept. So, a collision resolution scheme is necessary. We will talk about this collision resolution in just touch upon it in this module and talk a lot about it in the next module. So, here we are going to talk about let us understand what we mean by this. We will take dictionary as an example, because that is a direct understanding you can have of hash table. So, you have, when implementing a dictionary with a hash table, the goal is to store the item k comma 0, where k is the key and O is the object, at an index. The index is determined as I, which is nothing but the hash mapping or hashing to the key. So, you have an object, you have a key associated with the object, and that key is hashed using a hash function. So, let us assume the items are given there, Ram, Lal, Sam and Kala, with key values as some 20, the key values are given there. So, that is the key of the items, and the key is given to a hash function, and the hash function hashes, we are not, just take it as a black box for now, and the index of the hash table are normally called buckets. So, here we have, for example, Ram has been hashed to the bucket 3 and Sam to 6, Kala to 7 and Lal to 4. So, this is the hashing that has happened, and how that hashing gives you these values. So, remember what we have an object, associated with that object you have a key, and associated with the key you have a after that you take the key and then apply a hash function to it to get the index into the hash table. The index of the hash table is normally called as buckets. So, the size of the hash table is nothing but the number of buckets. So, that is the term used, and this is how it will happen. How that hash function does this, we have not yet explained. Now, the idea is this: use a function h to compute the slot for each key. So, that is what that slot or bucket for each key, and store the element in that particular slot. So, that is h of k. Remember, k is the key to the item. Okay. So, a hash function h transforms a key into an index in the hash table. So, suppose you have the keys, it is mapped on to a function, the table size is 0 to m minus 1, and the hash function will take the u is the number of keys into a, it will map it on to the slots 0 to m minus 1. So, that is what it does. Okay. So, we say key k hashes to slot h of k. So, h of k gives you that slot. So, advantages are, you reduce the range of array indices in m instead of the size of u, which is the key size, the number of unique keys or whatever key size, and storage is also reduced. So, that is the idea behind the whole thing. So, for example, you have a universe of keys, that is then all the keys put together. Then you have the actual keys, you will not know what keys are going to come. So, you will have to put a array size of universal keys, which you are not doing now. So, instead of that u size, we are trying to take 0 to m minus 1, which is the size of the table, hash table, the size of the slots or the size of the buckets, number of buckets. And you take each key, the actual keys, and map it on to, using that hash function, map it on to different slots. You would notice here that two keys k2 and k5 are both hashed to the same slot or bucket. We will come back to this later. So, this is what does. Now, what are the problems here? You have to find that slot, okay, key slot you have to find. So, this is the example of a hash table. So, some applications of hash table are database systems where efficient random access is necessary. You provide a way to locate the data in constant time. So, that is very important in a database application. Data dictionaries, it is a direct dictionary operation. So, adding, deleting and searching for data. If you do searching, especially hash table is a very efficient way of doing things. And then symbol tables, again where you have a table. For efficient implementation, compilers use this hashing to store the symbols. And network processing algorithms, for root lookup, packet classification, network monitoring, you normally use hashing. So, you will see that hashing is used wherever there is a lookup necessary. So, database system, data dictionaries, symbol tables and compile application network. So, many of the computer science subjects or topics do require the use of this lookup, and whenever you have lookup, hash table is a good way of doing that lookup. So, that is what we are trying to say. Now, let us look at the issues. Now, I very conveniently and magically said that h of the key will provide you a slot. Now, how is this h? H is a function. So, how do you, that is called the hash function. So, you need a method to convert the key to an index in the hash table or that h, and it should have some nice properties, because the indexing should come out properly. So, for that we need some properties. So, let us look at that. Now, sometimes what happens, more than one key will map on to the same index, okay, or the same slot or the same bucket, and that is called as direct access table. There are several methods to solve this collision. Okay. This collision, what is collision? Collision is that two keys, you are using a hash function to map the keys onto the slots or the buckets, and two keys hash value, two keys would index to the same bucket, then you say a collision has occurred. And there are many different ways of this collision detection method. If you do not use a collision method, then it is called direct address table. So, the methods of overcoming this collision or solving collision or collision resolution is to put the elements of the hash in the same location, but in a linked list, that is called chaining. Then there is another method called open addressing. If a collision occurs, you find a method to find another location for the key in the same table. So, that is another method. We will come in this part of the collision, and this we are not discussing in this module in detail. Here we are going to talk more about the hash functions. Okay. So, let us look at the hashing algorithm. So, hashing algorithm or the hash function will, what will it do? Convert a search key to an integer called the hash code. So, we are now dividing hash function into two parts, I will come to that. So, you convert the search key is nothing but the key associated with the object to an integer, and that, because you are going, why are you doing this? To get an integer to find a slot number in the table called the hash code, and compress the hash code into a range of indices for the hash table. Okay. So, you are trying to find a h of a function which gives you integers, and that integers has to map or compress that hash code into a range of indices for the hash table. So, that is what we are doing in the hashing algorithm. So, two parts, hash code and compression code. So, the typical hash functions has two steps. One is the search key to the hash code, and the second is the hash code, compress the hash code to a smaller range, so that it fits into the table. So, this is the two steps we are going to do in the hashing algorithm. Now, let us look at the hash functions. So, as we already told you, hash tables use of hash function h to map the input key to a unique location in the table of size m. That is what the hash function, the whole hash function does, or the hashing algorithm does. Let us assume that you have what you want to do is use a universal set of keys, you want to map it to the table which has size m. So, 0 to m minus 1 integer values you want to map, this is the mapping you want to do. So, this hash function will determine the hash table size, okay, what is the value that comes, and the integer h of x is called the hash value of key x. So, key, you have a key k or x, and the h of x, that hash function h that you use for mapping from the universal key set to the hash table location in the hash table, that h of x is called the hash value of key x. An item with key k will be put in that particular h of x or the integer or the slot in the table. To find an item key, you have to first check the location h of k. Okay. Now, as we already told you, a hash function is usually specified as the composition of two functions. So, previously we just spoke about a hash function, we did not say how it is composed. We want, given a key, we want finally we want a index into the hash table, that is what we want to find, the location of the key in the hash table, that is what we want. Now, a hash function is usually specified as a composition of two functions. One is the hashcodemap, which we spoke before, that is which maps h1, which maps the keys to the integers, and the compression map which is h2, which maps these integers into 0 to n minus 1 or m minus 1, that is the size of the hash table. In the previous slide what we spoke about was the direct, that is h is composed of h2, but there we said h maps the universal set of keys to the table slots. Here we are splitting that into two. One is h1 map, which is called the hash code map, is a function that maps keys to integers, and the second h2, the function h2 or the compression map, maps these integers into the table slots. So, the hash code map is applied first and then the compression map is applied. So, the result is h of x is nothing but h2 of h1x, because h1x is first applied, x is the key, h1x is applied and then h2 of h1x is applied, and that is your final h of x. So, the goal of the hash function is to disperse the key in an apparently random way. Now, we are coming to the property of the hash function. Hash function is normally a combination of hash code and compression, hash code map and compression map. Finally, the function of the whole hash function is to disperse the keys randomly in the table, that is our in a random way, that is our property. Now, we are going to define the hash functions. So, as already we told you, it consists of two functions. First find the hash value or the hash code map and then map it on to the given range. So, if you take this, you will have the object, then you map it on to integers and that integers to the range. So, you have keys to integers, integers to the table. So, two separate functions are used, one is called h and one is called hm or h1 h2. Let us look at the desirable properties of hash functions. Now, a good hash function should minimize collisions. I already told you what collisions are. When two keys map to the same location, you want to minimize. It must be easy and quick to compute. Okay, it should be easy and quick to compute, obviously, because you should not take too much time just to do that, and then it should distribute the keys randomly in the hash table. This is a very important property. So, I have different key values, everything should not be put together in the same location. So, as far as possible it should be randomly distributed. So, a good that is the meaning is it should be evenly spread the keys to, and any special structure should not be followed. So, it should be random, in other words. The key idea behind hashing is to simulate the randomness using a hash function. So, that is what we are finally trying to do. The hash function is trying to generate or simulate that randomness, and we always use the information provided in the key to generate this hash function. So, the information in the key is also important. Now, remember the hash function consists of two parts, one is hash code map and the other is compression code map. So, you have the hash code map, it should be fast, ideally of the order of each query should take 1, hash value must be deterministic, that is very important. It must always return the same integer each time, it should not give different values. So, it must be deterministic, and equal objects, if you have equal objects it should hash to equal values, otherwise the whole setup will not be proper. So, in other words, if you tell it x is equal to y, they are the same objects, then h of x are keys, in other words h of x should map to h of y, or they should be equal. If two objects are randomly chosen and there is only one, this is the property 1, there should be only a 1 in I chance, I is the number of bits that you are using for the integer representation, that they have the same hash value. So, given two randomly chosen objects or keys, there should be only a 1 in I, not 1 in 1, 1 in I is the size of the integer representation, that they map to the same value. So, distribution of hash value should be approximately even, either it should have a uniform distribution or a Poisson distribution. That is the necessary properties of the hash code map. Remember, the hash function consists of two components or two functions, one is the hash code map and the other is compression map. Hash code map was mapping the hash key values to an integers, and compression map is mapping those integers into the range, that is the range of slots or range of numbers 0 to n minus 1 or n minus 1, which is the n, where n is the size of the hash table. So, again it should be fast, it must be deterministic, the same thing. So, suppose you have n and m and hm of n, m is the size of the table, must always return the same value, that is the meaning of deterministic. If two integers are randomly chosen, there should only be a 1 in m chance that they have the hash value, the same thing that we told there I was the integer representation. Here we are saying m, what is m? M is the size of the hash table. So, there must be only 1 in m chance that the same randomly chosen integers here will map to the same value. So, the properties are similar, and it must create an even distribution or 0 to m minus 1. There should be no clustering, that is all the integers should not be clustered to the same near each other, it should be evenly distributed. So, that is important. So, now we have looked at the two properties of the two functions that we talked about, hash code map and compression code map. Both have approximately we need the same properties, it should be fast, okay. It should have it be deterministic, and it should be evenly distributed. The first one we say randomly, and here we are saying evenly distributed. So, this is the idea of the two functions. Now, we will go into the two functions. Let us first talk about hash code maps. So, reinterpret the memory address of the key object as an integer. So, how do we get that integer value? So, you reinterpret that as a integer. It is good in general except for numeric and string key. So, one way of generating the hash code map. You can do an integer cast. What do you do here? Reinterpret the bits of the key as an integer. So, you have bits there. So, those bits you can interpret as an integer. It is suitable for keys that are of length equal to or less than the integer type. Remember what we did in the first hash code map is taking the key and mapping it to integers. So, how do you do this mapping is what we are talking about now. So, memory address is one thing, reinterpret the memory address of the key as an integer. So, that would give you an integer, or the bits of the key you can take as a integer, but the problem is that size should be equal to the number of bits that you are using to represent the integer. So, that is called integer cast. So, component sum you can take, you can partition the bits of the key into components of fixed length, say 16 or 32, and sum the components ignoring the overflow. This is another method of forming the, we are talking about mapping keys to integers, remember, suitable for numeric keys of fixed length greater than or equal to the number of bits. So, if you have just lesser than the number of bits, no problem. If the numeric is greater than, but fixed length greater than the size of the integer type, then you will have to do this component sum. You can also do polynomial accumulation, partition the bits of the key into sequence of components of fixed length like 8, 16 or 32, and say you have a0, a1, an minus 1, that is the partition. Then evaluate the polynomial of p of z is equal to a naught plus a1 z plus a1. This a, remember a naught, a1, a2 are all the components of the in the bits of sequence in the key, and you use a fixed value of z ignoring the overflows. This is just a value of taking a function to map the keys to the integers. So, this is another method especially suitable for strings. The choice of z is equal to 33 for example, gives at most 6 collisions in a set of 50,000 English words. So, this is one very good way for strings. This is called polynomial accumulation. So, what are the types we saw? We saw memory address directly mapping or integer mapping, or we saw component sum, and then we saw polynomial accumulation. Let us take this. This can be evaluated in of the order of n using Horner's rule. So, the following polynomials are successfully computed, each of the previous one in 0 1. So, this is the way it will do, each it will calculate in 1, and so you can do it of the order of n. This is just the Horner's rule. So, where we have p of z is equal to p of n minus 1 z. So, other common hashing functions are truncating. So, suppose you have this value map to a table of 1000 addresses only, then pick 3 digits of the key randomly, that is one way. Folding you can do, and then take the fold and take, this is a very common way of doing it, fold and take the mod. You can do squaring also, square the key and then truncate. Radix conversion also you can do, you take 1, 2, 3, 4, treat it as base 11 and truncate if necessary. So, these are different methods in which hashing functions has to be computed fast, it has to be deterministic, it should distribute the integers, I mean random distribution should be there for the values. So, this is the conditions that we say. So, now let us look at compression maps. What we saw was hash code map, that was converting of the keys to the integers. Now, we have to convert the integers into the range of 0 to m minus 1. So, you can do division h2 of y, this is the second component of the hash function. So, y is the integer. So, you take, remember you have got input as integer. So, h2 of y, that integer is equal to y mod n. This is a very very common operation that they do, this is called division. The size n of the hash table is usually chosen to be prime. So, we are the people who are choosing the hash table size, usually chosen to be prime, so that this works out properly. Another method is multiply, add and divide, which is called as MAD. Here you have a y plus b mod n, okay, where a and b are values that you choose, non-negative numbers, and you can choose it in such a way that a mod n is not equal to 0, otherwise every integer would map to the same b. So, that you will try to choose such that a mod n is not equal to 0. You can choose a and b appropriately. So, this is called ay plus b mod n. So, this is another, remember this is to map the integer y to the values n. So, what you need y mod n, because you need to get a value between 0 and n minus 1. So, another method is called universal hashing. In practice, keys are not randomly distributed. We want them to be randomly distributed, but they are not randomly distributed. So, any fixed hash function might finally land up with of the order of n. So, hash functions that produce random table indices irrespective of the keys. What we want is, the universal hashing is trying to say that sometimes if the keys are not randomly distributed, you may land up with a hash function which yield finally of the order of n. Now, we do not want that. So, we want hash function that produce this random table indices even irrespective of how the keys are distributed. So, that is the idea. So, select a hash function at random from a design class of function at the beginning of the execution, and so a family of hash function is universal. So, now we are trying to define a function. Why is it called universal? This set of function, because irrespective of the distribution of the key and how the keys are, that is not in our hands, right. It will produce a function that gives you a randomness. So, the family of function is universal if for any ij, remember 0 to m minus 1 is the size of the thing, any values, the probability of h of j equal to h of phi is less than or equal to 1 by n, that is hashing to the same value. Choose p as prime between m and 2m and randomly select 0 less than a less than p and 0 b and define this h of k equal to a of k plus b mod of p mod n. So, this is one method by which where p is a prime between m and 2m. Remember what is m? M is the size of the table and 2m is twice. So, between those two you choose a value prime and choose a and b between those values, and then you decide the h of k. So, this they have found will give you a random distribution of the integer irrespective of what the integers are, with the integers you have got from the. So, this is a set of hash functions. You choose a hash function randomly and you map it to the this is the to the hash table. Okay. So, the definition of the universal hash function is given like this, where h of k you want to map that to 0 to m minus 1. Given a set, you have to choose the one that will give you this. H is the number of elements in H and the, that is the cardinality of H. So, that function is said to be, that is H is equal to h of k, where h of k is equal to the mapping of the universal to the universal key set, I mean that set to the key to the value of the. So, this property is very useful because the probability of collision is only of the order of 1 by m, and the main result is the chance of collision between distinct keys k and I is no more than 1 by m chance of collision if location h k and h I are randomly and independently chosen from the set, okay, from the set this. So, this how do you design a random function? Choose a prime value number p larger than whatever that range is, and you try to find the values and you define the function. We have already seen this. The family of all such function will have this property. So, this is what this class of function h of p m is universal. So, this we have already discussed before. This is how it is designed, and a and b is will be randomly chosen at the beginning of the execution, but there is some criterion that you have to choose a and b. So, let us take an example. Let us assume p is equal to 17 and m is equal to 6. So, h of a b k is equal to a k plus b mod p mod m. So, here we have, let us assume we want to we have 3, 4 and 8 is the key, and now a is 3, that is what a is chosen as 3, b is chosen as 4 and it has to be less than 6. So, 3 into k 8 plus b 4 mod 17 mod 6. So, this is mod m. So, this is how you will get, and it will map like this onto the value 5. So, you have that k 8 mapping to the model 5. The idea is this mappings of any values of k will give you a value that is randomly distributed. So, the advantage is it provides good results on an average independent of the keys, that is the idea of universal hashing, and guarantees that no input will always elicit the worst case behavior whatever may be the properties of the keys. Poor performance occurs when the random choice returns an inefficient hash function. This has very small probability. So, that is the idea, and the summary of this particular module is we explain the concept of a hash table and discuss the hashing algorithm and the hashing functions, and we spoke about the desirable properties of hash functions and the necessary properties of hash code maps and compression maps, which are the two functions that constitute the overall hash function, and explain the different aspects of universal hashing and the importance of hashing. In the next module, we will be talking about collision resolution. So, this is the module that we spoke about, basically about the hashing and the hashing functions basically. Thank you.